So for the last week or so, we've been dealing with trust analysis. So finding internal members in each member in a nice big two-dimensional trust structure. Today, we're actually going to extend that into 3 dimensions. And so we're going to try and look at finding internal member forces in a whole bunch of three-dimensional trust structures. So anytime we have something that's not nice and planar, so everything we've seen the last couple of weeks has been kind of this planar, two-dimensional trust structure. Anytime something is not nice and planar or nice and symmetric in the third dimension, we have something called a space truss. So space truss is essentially the three-dimensional version of everything we've already seen. And so we saw when we did our truss analysis in 2 dimensions that these things were built out of triangles for stability purposes. Just triangles are more stable than rectangles. So same thing here, simple truss structure in 3 dimensions, simple space truss will be made up of essentially 3-dimensional triangles called tetrahedrons. And so it looks something like this structure here. So this is kind of the simplest space truss. And then I can add on more and more of these to make a more complex space truss. And again, here, the point is to find the internal forces in all of these members. And so the procedure is pretty much the same as what we saw in 2 dimensions. So for our assumptions, we want to have it so that each member is in pure tension or pure compression. So again, whichever way that member is going, that's the same way the internal force is going, either inwards or outwards, compression or tension. And so to have that happen, we need a few certain things to happen. Again, same as what we saw in 2 dimensions. Any external force is applied at the joint, so I don't have any forces between joints acting on members. Each joint is going to consist of a ball and socket connection. So a ball and socket connection is basically a 3-dimensional pin connection. So it's going to allow rotation, but it's not going to allow any movement X, Y, or Z directions. And then the weight of the members is neglected as well. And so that should be enough to make every member be in pure tension or compression so that the forces lie on the same direction as the members themselves. And then you can use either method, joints or sections, just like we did in 2 dimensions. Joints is useful if you want all the member forces. Sections is useful if you only want a certain amount. So same sort of thing is going to happen for each of those. Same kind of procedure. So method of joints, again, same procedure. I look at each individual joint. So I isolate one particular joint, and then I draw the free body diagram where each member is replaced by some internal force going in that same direction. In this case, because we're dealing with 3 dimensions, I have 3 equations of equilibrium. Forces in the x direction equals 0, forces in the y direction equals 0, and forces in the z direction equals 0. So I can have actually up to 3 unknowns. 2-dimensional method of joints, you can only have up to 2 unknowns. So in this case, I can actually have up to 3. But don't have any moment equations because, again, each joint is just one single point. One single point does not have rotation. So very similar method of joints. And similarly, very similar method of sections. Method of sections, I come along and I cut this thing into 2 pieces. So I cut through a certain number of members and then throw away half my structure. On the other half, I replace whatever member I cut through, replace it with some internal force going in that same direction, and then do rigid body equilibrium on whatever's left over. And so in this case, 3-dimensional rigid body equilibrium, I have 6 equations of equilibrium, all my 3 force equations, x, y, and z, adding up to 0, in addition to moments, moment in the x direction, moment in the y direction, and moment in the z direction, all adding up to 0 as well. And again, those can be taken at any point I want. So 6 total equations of equilibrium in this case. So I can actually solve for up to 6 unknowns per section cut. So every time I cut it, instead of only being able to solve for 3 things like I did in 2D, I can actually solve for 3 things. So you may be kind of worried that these things are a lot more complicated in 3 dimensions than 2 dimensions. And yeah, the geometry does get definitely messier. So there is some more complications there. But as we just saw, you can actually solve for more things per joint or per section cut. So instead of only being able to solve for 2 things per joint and then moving on to the next joint, solving for another 2, and so on and so on, I can actually solve for 3 each time. So that speeds up the process. Same thing for section cuts. Instead of only solving for 3 things, I can actually solve for 6. So that speeds up the procedure quite a bit and kind of counteracts this more difficult geometry. So hopefully, when we go through examples later today in class, you'll agree with me and see that's not actually that much worse than 2D.